you have seen a program crash. You have debugged a value that mysteriously changed from 42 to 0, and you spent hours tracking down which line was responsible. What if I told you that a single keyword could prevent entire classes of those bugs, enable extreme performance optimizations, and even change when your code runs? Today, we are going to explore how C++ gives you unprecedented control over data mutability and execution timing. This directly impacts your program's reliability and speed, turning those mysterious crashes into predictable, robust behavior. This is not just about syntax. It is about fundamentally changing how you reason about your C++ code. By the end of this, you will be able to differentiate const, constexpr, consteval, and constinit by their compile time guarantees and use cases. You will apply const correctly to variables and pointers to enforce immutability and improve code safety. You will leverage constexpr functions and variables to enable compile time computation for performance and constant contexts. And finally, you will utilize C++20's consteval and constinit to ensure strict compile time evaluation and prevent static initialization order issues, which are a notorious source of hard-to-debug problems in larger C++ projects. This is a lot to cover, but each piece builds on the last. When I first started, I thought variables were simple, a named box holding a value. But the real challenge, especially in larger systems, is managing mutable state. Imagine you have a shared whiteboard in the office. Anyone can walk up and write Project Alpha deadline, Friday. Then someone else comes along, sees the board, and writes Project Alpha deadline, Monday. Now, if you look at the board, what is the deadline? It depends on who wrote last and when. This is mutable state. In a program, a variable, like an integer max connections, can be changed by any part of your code that has access to it. If one function sets it to 100 and another, perhaps unexpectedly, changes it to 10, your entire system's behavior shifts. This diagram illustrates the problem. Data flows through different functions, and each function has the potential to modify it. Without clear rules, tracking down an incorrect value becomes a nightmare. You are essentially playing detective, trying to find the one line that altered the state in a way you did not expect. This is where our first keyword, const, comes in. Think of const as a lock. Once you put a value into a variable and declare it const, that value is locked down. No one can change it. This is not just a suggestion. It is a guarantee enforced by the compiler. The const keyword marks a variable as read-only after its initialization. This communicates intent to both the compiler and other programmers. The compiler then enforces this const correctness, catching accidental modifications at compile time, not at runtime. This means you get an error message before your code even runs, saving you from hours of debugging. It is a fundamental tool for building robust, predictable systems. Let us look at a simple example. Here, I declare an integer called max connections and set its value to 100. I then mark it with the const keyword. This tells the compiler that max connections will always hold the value 100. If I then try to assign a new value, say 200, to max connections, the compiler immediately flags it. You will get an error message like error: assignment of read-only variable max connections. This is exactly what we want. The compiler is your first line of defense against unintended state changes. Now, const with pointers requires a bit more care because you have two things that can be const: the pointer itself or the data it points to. The trick is to read the declaration right to left. If you write constant star p semicolon, this means p is a pointer to a constant. The integer cannot change through p, but p itself can point to a different integer. Conversely, in star const p semicolon means p is a const pointer to an int. Here, the pointer p cannot be changed to point to a different memory location, but the integer it points to can be modified. And if you want both, you write constant star const p semicolon, which means p is a const pointer to a constant. Neither the pointer nor the data it points to can change. Here is a common mistake. I declare an integer value set to 10. Then I create a constant star ptr, a pointer to a constant integer, and make it point to value. If I then try to dereference ptr and assign it a new value, say 20, the compiler will stop me. You will see error: assignment of read-only location star ptr. This is because ptr promises not to change the integer it points to. However, I can still make ptr point to a different integer, another value, because ptr itself is not constant. If I had declared int star const ptr equals ampersand value semicolon, then ptr const ptr equals ampersand another value semicolon would be the error, but star ptr const ptr equals 20 semicolon would be fine. Another point of confusion is how const behaves with function parameters. If I define a function print value that takes const int x and then call it with an integer myval set to 42, the const on x only applies to the copy of myval that print value receives. The original myval remains mutable. In fact, constant and int are considered the same type in function parameter contexts when passed by value. This is because the caller's argument is copied anyway, so preventing modification of the copy does not affect the original. The const here prevents accidental modification of the local copy within the function, which is still good practice. Now that you understand const, constexpr is going to make perfect sense. Think of constexpr as a special calculator that runs before your program even starts. While const guarantees immutability, constexpr goes a step further. It indicates that a variable or function's value can be computed at compile time. This is a massive optimization. Instead of performing a calculation every time your program runs, the compiler does it once, during compilation, and bakes the final result directly into your executable. This reduces runtime overhead and allows values to be used in contexts that strictly require constants, like array sizes or template arguments. Let us see this in action. I declare a constexpr int called val and assign it the result of 5*5. Because both 5 and the multiplication operation are known at compile time, the compiler will calculate 25 and store that value directly into val. The crucial part is the next line, int arr left bracket val right bracket semicolon. You cannot declare a C-style array with a size determined at runtime. It must be a compile time constant. Because val is constexpr, the compiler knows its value is 25, so this array declaration is perfectly valid. If val were just a constant initialized with a runtime value, this would be an error. Functions can also be constexpr. Here, I define a constexpr int square left parenthesis int x right parenthesis function that simply returns x star x. When I call square left parenthesis 5 right parenthesis and assign it to constexpr int compile time val, the compiler can evaluate square left parenthesis 5 right parenthesis to 25 at compile time. However, a constexpr function is not guaranteed to execute at compile time. It can also be called with runtime arguments. If I declare int runtime arg equals 7 semicolon, and then call square left parenthesis runtime arg right parenthesis assigning it to int runtime val, the function square will be evaluated at runtime, just like a regular function. The constexpr keyword only indicates the possibility of compile time evaluation. The common mistake here is assuming that constexpr always forces compile time evaluation. It does not. If you have a constexpr function, say add 1 left parenthesis int x right parenthesis left brace return x plus 1 semicolon right brace, and you call it with a variable whose value is not known until runtime, like int input val equals get user input empty parenthesis semicolon int result equals add 1 left parenthesis input val right parenthesis semicolon, then add 1, will run at runtime. The compiler only evaluates a constexpr function at compile time if all its arguments are constant expressions and its result is used in a constant context. If any of those conditions are not met, it falls back to runtime execution. This flexibility is powerful, but it means constexpr is a promise of capability, not a strict command. Here is where it gets interesting. With C++'s consteval, if constexpr is a polite suggestion, consteval is an absolute command. Think of consteval as a bouncer at a club. If you are not on the compile time guest list, you are not getting in. A consteval function is an immediate function. Every call to it must produce a compile time constant. There is no runtime fallback. If you try to call a consteval function with an argument that is not a compile time constant, the compiler will issue an error. This is incredibly useful when you need to guarantee that certain computations are performed at compile time, perhaps for security, performance, or to generate metadata. Let us define a consteval int compile square left parenthesis int x right parenthesis function. When I call compile square left parenthesis 5 right parenthesis and assign it to int a, this is perfectly fine. The argument 5 is a compile time constant, so the function is evaluated at compile time, and it gets the value 25. Now, if I declare int b equals 5 semicolon, and then try to call compile square left parenthesis b right parenthesis and assign it to int c, this will result in a compilation error. Even though b holds the value 5, it is not a compile time constant expression. The compiler will give you an error like error : call to consteval function compile square is not a constant expression. This strictness is the core of consteval. The common mistake with consteval is trying to use it in a context where an argument is not a compile time constant. You might think, well, I know b is 5, so it should work. But the compiler does not care what you know. It cares what it can prove at compile time. If b could potentially change before the function call, it is not a constant expression. This means any variable whose value is determined by runtime input, or even a non-const local variable, cannot be passed to a consteval function. You must ensure all inputs are themselves constant expressions, or you will hit that compile time error every single time. Finally, we have C++20's constinit. This keyword addresses a very specific, insidious problem in C++, the static initialization order fiasco. Imagine you have two global variables, A and B, in different translation units. A uses B in its initialization, but B might not be initialized yet when it tries to use it. This leads to undefined behavior. The constinit keyword ensures that a variable with static storage duration is initialized at compile time. This completely bypasses the static initialization order problem because the variable is ready before any dynamic initialization can even begin. It is like pre-baking a cake before the party starts, so it is ready exactly when needed, no matter what else is happening. Here, I declare a constinit int global equals 42 semicolon. This is perfectly fine. The value 42 is a compile time constant, so global is initialized at compile time, guaranteed. It will be ready before main even starts, and before any other dynamically initialized static variables. However, if I have a function compute empty parenthesis that returns an integer, and I try to declare constinit int bad equals compute empty parenthesis semicolon, this will be a compile time error. The compiler will tell you error : bad must be initialized by a constant expression. Compute empty parenthesis is a runtime function, so its return value is not a compile time constant. The common mistake with constinit is trying to initialize a static storage duration variable with a value that is not a compile time constant. Remember, constinit is about guaranteeing compile time initialization. If the value cannot be determined at compile time, constinit cannot do its job. This means any function call that is not constexpr or consteval, or any variable whose value depends on runtime input, cannot be used to initialize a constinit variable. It is a powerful tool for preventing a specific class of bugs, but it requires its initializer to be fully resolvable by the compiler. You now understand exactly how to use const to enforce immutability and catch accidental modifications at compile time. You can leverage constexpr to enable optional compile time computations for performance and constant contexts, knowing when it will and will not run at compile time. And you have mastered the C++20 additions, consteval for strictly enforcing compile time evaluation, and constinit to guarantee compile time initialization for static storage duration variables, effectively eliminating the static initialization order fiasco. These keywords give you fine-grained control over your program's behavior and performance. Next time, we will dive into type deduction with decltype and type aliases, exploring how C++ can automatically determine types for you, and how to create convenient aliases for complex type names.